Welcome back. This is A level computer science 9618 paper 2, and this is part 4. So in this video we are going to understand about abstract data types. So abstract data types, which means abstract data type comes in data structures, and data structure means a particular way of storing and organizing data. So a particular way of storing and organizing data in a computer so that it can be used efficiently. So data structure, when we talk about data structure, we are talking about arrays, files, linked lists. That we're going to understand what is linked list, what is stack, queue, trees, binary tree. Okay, it's in P4, don't worry. Graph and so on. So this is what data structure is: the structure of the data and organizing the data in such a manner that we can use it more efficiently without wasting any memory. It's all about coding. I'm talking about coding, right? So whenever we try to store data and we are trying to code something, right, we are storing the data in a file, and let's suppose we want to retrieve the data from that file. So filing comes in data structure. When we are storing data in an array and we are try to manipulate the data through arrays, we can also organize or manipulate the data through linked list, stack, queue, which you're going to understand what are these. So linked list, stack, queue are abstract data types. Okay, so these are abstract data types. So what is meant by abstract data type? It means that it's a concept that can be applied anywhere. It can be applied anywhere. It doesn't matter which language you are using, whether you are using C language or Python or VB or Java. So it's a concept that can be used anywhere. That is the meaning of abstract. Okay, so abstract data type, or you can call it ADT, it's a collection of data and a set of operations. So how you are collecting the data and what are the operations that you can perform on those data. Okay, so stack, queue and linked list are some of the example of ADTs. Okay, so abstract data types are entities that are the definition of data and operation but don't have implementation. Why do we don't have implementation? Just like I told you guys, because there are so many different languages. For example, in C language, the data structure will be implemented using structure concept, record structure that we have just understood in the part 1, right? Record structure, it's also in C language, and C language is not object oriented, it's not OOP, but Java is OOP. Okay, so when we try to make linked list or stack or queue, we use if we are using C language, then we might go through procedural language, which means there is no object and class concept. Okay, and we would have to use structure concept or array. But in Java is an object oriented programming. Java, Python, okay, C sharp, these are all object oriented programming. You can call it OP, and we will cover this in P4, don't worry about it. For now it's P2. It's more like you are touching the concept of linked list, stack or queue. You will not be asked to write code of any of these three. So for now you just need to understand what are abstract data types and where do we use linked list, stack or queue, and how to use it, how do we perform the operations on those data which are being stored in those data types. Okay, so abstract data type means that it's a concept that can be implemented. It's a concept that can be applied anywhere. It doesn't matter which language you have. So it's a concept, okay, that how you are storing the data. For example, let's talk about array. So if we see in abstract logical point of view, we know that an array have store a set of elements of int type. It can store any kind of data types, right? Int types, string, int, boolean, whatever. It can read elements by position, or you can call it the index. Okay, so it can, and we can modify element by the index, and we can perform sorting as well, bubble sort, and so this is abstract logical. This is logical point of view. We have understood that this is an array. We will access this through an index, and we will try to delete or insert or modify or do sorting, all of this stuff. So it's a logical. Now we need to implement it. So it depends on the language. If I'm try to using in VB code, then I will write in this way, or if it is Java, it will have a different syntax. If it is C language, it will have a different syntax. So that is the meaning of abstract. Okay. So what is the difference between, okay, so we will start with linked list. For what is the difference between an array and a linked list? Array is static, which means it is the size of the array is fixed. Okay, so it has a fixed size. So when we try to declare an array, we will give the user defined data, okay, built-in data types, and we will try to give the value that how much value it can store. We will give the size of the array, so it will be fixed, it cannot be changed, okay, depending on inserting any more extra values. But linked list can be changed, it is dynamic. The more we add, the more these nodes will be created. These are nodes, okay. Let me, so if I'm talking about linked list, so linked list consists of a collection of nodes. So nodes means that this is a node, okay. This node contains an address, like for example 001, okay. It contains a data or content or anything, it is storing a data, and this is the pointer, it's pointing to the next node. This is a pointer, okay. So this whole thing we call this a node. Wait, let me use a different color. So this is a node, okay. So these are all nodes. This node is pointing on the address of this node, and this node is pointing on the address of this node, and so on. So this is the head pointer, this is the tail pointer, and this node will point to null, the null value, okay. So the difference between array and linked list. So the size of the array is fixed. Array elements need contiguous memory location to store their values. They need contiguous memory locations to store their values, okay. Inserting an element in an array is performance wise expensive, which means it is because if we try to insert an element in an array, then we will automatically would have to shift those elements backward and forward. For example, if you are inserting an element or deleting an element, so what will happen that you will have to shift those elements, the remaining elements left or right, okay. So this is how it's happening. As for linked list, it is dynamic memory allocation, okay. So it is dynamic, which means memory allocation is done by okay. It allows dynamic memory allocation, which means memory allocation is done of the runtime by the compiler, and we do not need to mention the size of the list during the linked list declaration, okay. This is the concept of OOP. When we will go through object and classes, then obviously, so whenever we try to create a linked list, we can create using either through an array. We can create a linked list through an array, or we can use it. We can create this through OOP, okay. And for now, we just need to understand that how the linked list work, and what is a linked list, why do we use it, why it is better than array. So array, when we are making an array, a simple array, its size is fixed, okay. Any array element need contiguous memory location to store their values. They will have their own memory, okay. Contiguous memory location to store their memory. That it will be given a fixed memory, so that memory cannot be changed. So according to that memory, you will try to insert or delete the values, okay. So it's the size of the array is fixed. It is contiguous memory, okay. Inserting an element or deleting an element, when we try to insert or delete it, the remaining elements will have to be shifted left or right, okay, in order to fill the gap. Alright, but in linked list, it's a dynamic memory allocation. So whenever we try to add a new element, it will have its own a new memory will be created for it, okay, and it's dynamic. We can add as much as element as we wanted in linked list. Okay, so it allows dynamic memory allocation, which means memory allocation is done of the runtime by the compiler. Okay, you don't need to read all of that. It's a concept of P4. For now, you need to understand that it allows dynamic memory allocation. Okay, we do not need to mention the size of the list during linked list declaration. Okay, it's a concept of P4. Don't worry. This is a concept of P4. This is P4 concept. This is P2. You need to understand for now. This is P2. Okay, linked list element don't need contiguous memory location, obviously, since it's different, because elements are linked with each other using the reference part, pointing to one another. Each node is pointing to another node of the node that contains the address of the next node of the list. That's why. So we can add as much element as we can. Okay, so when we try to add an element, it will create its own node, and then that node will be put inside a linked list. Okay, each node is pointing to another node. We can inserting or deleting an element from the linked list doesn't require element shifting. That's the main advantage. It doesn't need element shifting, so the time complexity is very much low, okay, as compared for the array. Time complexity is another concept in P4. Don't worry. What I mean to say is that there's no element shifting. Okay, so it's much faster, it's much better than array. Only the pointer of the previous and the next node require change. For example, okay, you know what, we will go through this in the end. It does not waste memory space. Okay, so it does not waste memory space. It can grow and shrink at its size as per its requirement. You can delete as much as you can. You can add as much as you can. Okay, what are the use of linked lists? It can be, and you can implement this as in stack on queues, but in this P2 course we will not going to do with linked list. We will do with array. So we're going to try to implement this using arrays, and also linked list itself. We will try to implement this using array, because it's in P2 course. But in P4 it will be a completely different scenario. For now in P2 you just need to touch the concept at what are these, what is linked list, what is stack, what is queue, why do we use it, where do we use it, why do we need to learn all of this. Okay, so use of linked list, it can be used in music play. For example, you're going in a you're doing jogging and you're listening music, and one song is connected to, it's a list of song. You're listening each one. Songs in the music play are linked to the previous and next songs. It's a concept of linked list. It can be applied in here. Previous and next page in a web browser. We all know what is a web browser. Why do we have gone through this. Okay, previous or next page we do all the time. We can access the previous and next URL search in a web browser by pressing the back and the next button. Back and forth, we all know this, right? Since they are linked as a linked list, can be applied in here. An image viewer, previous and next image are linked and can be accessed by the next and previous buttons. Okay, so these were the application of a linked list. And how do we implement this? We can implement in OOP, but for now we will try to implement using arrays. A linked list can be containing several items in which each item in the list point to the next item node. In a linked list, a new item is always added to the start of the list. Okay, so we have this linked list. We have this, a node. We got the data. We got the pointer. So this is first when we try to add a first list. When we try to add a first element. Let's say it's an empty linked list and we want to add a string of names. We want to add number of names, right? For example, if I add Muhammad, I have added into the list. So now it contains Muhammad, and now this will become the head pointer. This is the head pointer, and then this node is pointing to null for now, right? Because I haven't put another element in here. Now if I add another one, like for example Abdullah, this for right now in before it was null, but then I will remove this null, and then another node will come. This will point to this, the address of this node, okay, and this will point to the null, okay. Then another data will come like Ali, it will have a data Ali, Muhammad, Abdullah, Ali. This then it was null, but then I decided to remove null, and now this node will point to the address of this node, and then this will point to null. So it will keep on going. When we add an element, it will create a node, and each and every node will have its own address. This node has its own address, and this address has been pointed by the head pointer. Head pointer means the starting of the list, okay, the starting of the linked list. Then this point to the next node, and this point to the next node, and this point to null. And this could be known as a we can have another pointer, the tail pointer, the end of the list. Okay, so this is the tail pointer, tail PTR. Okay, so linked list, new item is always added to the start of the list. I mean, adding each one, and each one is each pointer. For example, it was null, but now it's pointing to the next one. It was null, but now it's pointing to the next one. It keep on going dynamically. A linked list can be implementing using two 1D arrays, or we can use 2D arrays as well, I think. But in this course, you will try to understand how to use in two 1D array. We will use two different 1D arrays. One will be used for data, and the other will be used for pointers, so pointing each node. Okay, we will pretend that each index will be a node. It will contain a data and a pointer, okay, which a pointer means pointing to the next node. A linked list can be implemented using 1D or two 1D arrays, okay, arrays. One for the item in the linked list, and another for the pointers. One for the item, I mean the data, the content in the linked list, and another for the pointers, okay, to the next pointer to the next item in the list, and a set of pointers. The empty position in the array must be managed as an empty linked list. Okay, even though this concept is we are using this concept in array only. There's no such thing as an empty, I mean, okay, since we are using an array, and we all know that array has a fixed size, so those index which are empty, we'll try to separate those indexes, and we'll try to make an empty linked list, a different linked list. And those index which are filled with data, right, we will make that there will be two linked lists, one which is empty and the other which is filled. Okay, since we are dealing with array, we try to implement we try to make a linked list through array. Okay, it's in P2 for now. The empty position in the array must be managed as an empty linked list, usually called the heap memory, you can call it. This is how the linked list look like. The start pointer point to this node, this point to this node, and the address, this point to, okay, what's happening here? So right here we are, okay, this pointer is pointing to this node, and this node is pointing to this node. So again, this is the concept of linked list. Yeah, definitely, it doesn't matter. Actually, this is we are seeing this as an array, so it doesn't matter where the index are. We just need to point, so it's pointing this one is pointing this one, this one is pointing this one, this one is pointing this one. Again, it's a linked list. Okay, and this will be null. It's not pointing to anyone. This is a complete linked list. These are the data. This is a pointer pointing to the array, the address of this node. Then it point to this node, pointing, and it's not pointing anyone, so it's a null. This is a tail pointer. This is a head pointer, or you can call it a start pointer. But When you will go through P4, you will understand that this is known as head pointer, head PTR. Okay, this will be known as the tail pointer, tail PTR. Okay, and okay, so we have been given an array. This is 1D array. Okay, 1D for this, for the data, and 1D for the pointers. Supposing we have put okay, so we will start with this address of this node. Okay, I got this data, Alvaro, and I got the I'm pointing to the next node. I'm pointing to the next node. I got the another data. It's pointing to the next node now. Another node. It's pointing to this. Zoto, now it's pointing to this. Oliver, now it's pointing to this. Okay, now it's pointing to this, and yes, now it's the end of this link, end of the list. Okay, so first of all it was pointing to this, then pointing to this, and it point to this, then it point to this, and then it point to this, and now, so this is the end of the linked list. I mean, this is the end, this is the linked list. We have created a linked list of these content. The remainings are this one, this is empty, this is also empty, and this is empty, and this is empty. We have created a different empty linked list. Okay, so let's say it's starting from here. We have the empty node. Okay, I think I have made in here. Here you go. So I got, so this is a this is an empty linked list. Okay, so it's first of all the field, this is a field list pointer. It's pointing to this number 1, then it point to 5, then point to 7, it's pointing to 7, then it's point to 8, and now it's pointing nowhere. This is the empty linked list, and this is the linked list which we have created having data, you know. So there are two different linked lists when we are try to implement when we are try to make a linked list through an array concept, have it different 1D array, you know. So we know start pointer, head pointer, field list pointer, and null pointer, which means null. Okay, so this, my friend, is a linked list. Congrats. This is how it's look like. You are starting from here, then goes from 3, then 11. 11 is here, you know, it's going to here, then it goes to here, and then it goes to 1 again. It will come to 1 again, then 1 to 7, 1 to 4, 4 to 12, 12 to 9. Where is 9? There you go, 9, and then 0. Okay, this is a null pointer. This is the end of the linked list, and the remaining which are empty, it will form a different empty linked list. Okay, having a field list pointer which is 2. This would be the field list pointer, free list PTR. Okay, so this is the concept of linked list that we need to understand when we are using array to make a linked list. Okay, but in P4 it's again totally a different concept. When we are going through OOP, object oriented programming, we are making the linked list through classes and objects, constructors. Okay, so that's a real game. P4 is a real game. For now in P2 you're just touching the concept that how do we try to implement it, and how do we use it. Okay, now we have created the linked list. How do we try to insert or delete or append, do anything like that? For example, if I'm adding a new node to the beginning of the linked list, what will happen? This is the new node. Okay, this was the linked list, the initial linked list which was created. I have decided to add this in the beginning of the linked list. What will I do? I will simply change the head pointer, and I will point to this node, the address. Okay, then I will try to change this from null to pointing to this node, and there you go, we have created the linked list. When we are trying to add it from the beginning. Okay, what happens if we try to add in the middle? So this pointer will not point this, it will point this, okay, and then this point will point this, then it becomes a part of the linked list. What will happen if we try to add in the end of the linked list? It will, instead of null, this will point to this and this will become null. Okay, so this is how we are adding it. So yeah, okay, this is a linked list, that we have this linked list, and these are the free, these are the empty linked list. If we want to, according to when making an array, when making a linked list through array, okay, according to that, when we are adding a new element, we will try to select an empty element, an empty index from the empty linked list. For example, if we are, okay, this free pointer is pointing to this node, that this is empty, boy, you can use this, okay, make it as part of your family. So we have taken this out, and we just try to change this, instead of pointing this, it will point to this node, it will point to this node, and then this will point to this node, and then the free pointer will now point to this node. Okay, so this is how we are taking an empty index and then making part of the linked list. Okay, according to when we are making a linked list through array. Okay, okay, now it comes when deleting an element, when we are deleting it. For example, if you want to delete from the start of the array, we simply try to change the instead, for the head pointer to point this, we will just point this, and we will forget about this whole thing. And also we try to make this null. The head pointer will point this from now, and then this will become null. There you go, we have deleted this. Very simple. If we want to delete this, we'll just simply try to point this, and this will become null. If we want to delete the last, we will just going to make it null, and this will be gone forever. This is how you try to delete it. So there you go. We want to delete this, we're just going to point to this, we will make it okay, so the free pointer will point this, and this will point to the next empty element and the next empty index, and this will become part of the empty linked list. Okay, and the linked list will be updated. So this is the concept of linked list when we are making it through array. Okay, now let's move on to stack. What is a stack? A stack, which also more look like a list, similar to linked list, but it's a different approach. It's more like, for example, I have put books, one book after the another. I'm making a stack, and if I want to remove these books, first I will try to start removing from here, then from here, then from here, and then back to where I've started. Okay, so the approach is last in, first out. So last in, first out, when we are adding it, this becomes the last, but when we try to remove this, this will become the first. Removing the first element, which is on the top, removing this, then remove this, then remove this. I have made this right, I have removed this, now I will remove this, and then I will remove this, and then I have come back to where I have started. If I want to add, I will add, and it will keep on going like that. Okay, so item can be added to that stack, which is the concept of push. When you're doing push, which means you are adding the element one after the another and making a mountain, or making it look like a mountain of books, mountain of CDs, mountains of anything. Stack. Okay, items can be added to stack. Push, we will try to remember this as pushing it, which means we are adding it. Removed, pop. This is how I'll try to remember the operations. The first item added to the stack is the last item to be removed from the stack. Okay, when we try to add a stack one after the another, so the last the item which is on the top will be removed first. This is stack. So this is the base pointer, this is the top pointer. When we use the push, when we have the function as push, it means we need to add more, and when we use the function pop, which means we need to delete, and the pop means it will pop pop pop. Push means push 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 until it becomes full. Okay, so this is a stack. For example, if I've already filled this stack and I want to add more, this will give overflow error, which means the stack is overflowed, it doesn't contain any more space. But what if I wanted to empty this whole stack? Okay, what if I want to do that? So what will happen if I wanted to empty all of this, and then if I decide to I want to empty more, but then if it is good, it goes down, right? I'm for example, I'm using the pop function, pop 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 pop. Now it cannot be pop more, but still I just did pop, but then it will give an error. Underline stack flow, underflow, stack underflow, which means we cannot pop any more element because it's already empty. When we try to pop an element from an empty stack, it is said that a stack underflowed. It gives an error. If the number of elements exceed, okay, when we talk about stack overflow, underflow, overflow, when we talk about overflow, the number of elements exceed the stated size of a stack, the stack is said to be overflowed. Okay, so this is the concept of stack. So we have this pseudocode we will try to implement using array. So this is a size 1 to 10, declare stack array of integer having an integer as a data type, then declare top pointer, the base pointer, and such, and stack full. Okay, stack full, this is the limit. Okay, top pointer is 0, base pointer is 1. Top pointer 0 means this is null for now, since it's an empty linked list, so its top base pointer is pointing to the first index, pointing it from here. Okay, if top pointer is less than stack full, which means if there is space available, if it is not, if space available, that's what it mean by it. If space is available, if top pointer, this is the top pointer, is less than stack full, which is the limit, then top pointer is equal to top pointer plus 1. Okay, now it's incremented by 1, which means now it will come here, top pointer will come here. For before it was 0, but now since we have incremented, then it will become 1, and then we try to add an element, an item into that stack, which means now it's pointing, the top point is pointing this one, this first node, this first index. Now it will add an item, like for example 54, if it has added an item. Else, if for example stack is not full, if space not available, then stack is full, cannot push. And if this the function, should we will try to understand what is the function, but for now you can call it a method. This is a method of push. This is a pseudocode form. Okay, you just need to understand how this thing work. Pop means removing anything. If top pointer is equal to base pointer minus 1, what does that mean? Okay, if top pointer is equal to base pointer minus 1, for example this is a base pointer and the top pointer is, okay, base pointer minus 1, it is the value of the base pointer is 1, but then 1 minus 1 is 0. If top pointer is 0, which means it is null, it is out, which means the stack is empty, cannot pop more, the stack is empty. Okay, if the top pointer is equal to 0, the base pointer which is 1 minus 1 is 0, If the top pointer is 0, then you can say the stack is empty, cannot pop any further. Else, if it is not empty, you can keep on deleting it at okay, item is equal to stack top pointer. Okay, you have give the value to this, in you have transferred to here the value inside the stack. For example, if it was pointing to this, let's say 34, so 34, 28, 24, 65. Let's supposing this is the value that the top pointer is pointing at. Okay, 65. We want to delete 65. So what will I do? If top pointer is equal to this, then it is empty. Else, if it is not empty, if it is not equal to 0, else the value inside will be transferred to this variable. It was 65, it will come here 65, and then top point is the top pointer minus 1. Okay, so you just decided to, top pointer was here, right? Top pointer was here, you just decided to put in here. You're not pointing to this anymore, so you can just say that yeah, it is automatically deleted. Okay, since it's pointing to this one, the top point is the number of, telling the how many number of elements are present in the stack. So once we try to add an element from here, then it will be override by another value. For example, if I want to push, what will happen? If top pointer is less than stack full, okay, space is available, the top pointer is a top pointer plus 1, it will come again back again here, and then stack top pointer is equal to item. This will be overwritten by another value. This is how you try to delete in a stack. So this is how you try to push. Pop, push means add, pop means deleting an element inside a stack. This is a concept of stack overflow. This concept will also come in OOP, object oriented programming, or in Java when you try to do some programming. Okay, so yeah, the concept of stack comes in memory. Okay, it comes in so many different applications. It comes in calculation. For example, if you are making a calculator, there will be okay, we also try to use stack. Okay, when you try to making a calculator having different operations, having following a complete board mass, like for example this bracket 5 multiplied by 2 and then plus 6 and divide by 7. So each operator will come into the stack, so don't worry. This concept is in P4 though, but I'm just telling you anyway. Now we are coming to the concept of queue, linked list. What is meant by queue? You must have heard this word queue so many times in your life, right? For example, if there's a break in a canteen, the students are making a line, making a queue. First in, first out, first come, first serve principle. Having a bank, you're going to the bank, you're having list of people that who wants to, they are in a list, right? First, the one who will come first will be first served. Okay, going served line by line, first in, first out, first in, go, okay, first out. I mean, the person comes first in, it will be served now, first out, first in, first out. Okay, but in stack it was a different scenario. For last in, first out, last in, which means coming last, I mean coming here, but when we try to remove it, first out, first out, first out, first out. Okay, but in a stack it looks something like, having, since we are using array and we have values, so first in, first out, first in, comes adding each element, but when we try to remove it, it will start from here, first out, first out, first out, first in, first out, first in, first out, first in, first out, having a list of elements. For example, if I want to add 25, I have put 25, then 36, 48, 54. This was the first person that came into this array, so this will come out first, then it will come out first, then this one will come out first. So first in, first out. This is the concept of queue. Okay, so a list containing several items operating on the first in first out FIFO principle. Item can be added to the queue and removed from the queue using the first in first out principle. The first item added to the queue is the first item to be removed from the queue. Items are removed from the front and added to the end of a queue. Items are removed from the first, okay, and added at the end of the queue. Very simple, yeah, as we are following this scenario. The queue should be managed as a circular, should be managed or can be managed as a circular queue to avoid moving the position of the item in the array every time an item is removed. For example, whenever we try to remove, for example, okay, so let's take an example. Let's take this one. Supposing this is the queue and I have put a value, it's starting from here and here, but in stack it start from here. So having a front pointer, this is a start, and then you just keep on adding one by one, and this is the end pointer. This is a front pointer, end pointer. When we try to add an element, we will say include. It has been include, which means we have added an element. Include. Wait. Include. We have added an element. But if we try to remove any element, we will say dequeued. Okay, so that's the meaning. Include means adding an element, dequeued means removing an element. We can call it rear pointer or end pointer. You can also call it rear pointer. Okay, so you just first you try to add this one, then this one. If we want to delete an element, then we will start from here, first in first out, right? We add this, for example, a guy comes into this is a canteen. This is a guy waiting for the people to buy his food, right? This guy comes in having the number 27, that this guy comes, that this guy comes. We keep on adding up because people are keep on coming into people are making a queue. For example, this guy wants to make an order. In this for example, this is KFC. Okay, this one wants to order a burger. Then it will this will do the serving, first in first out. It will get out. So this one will be deleted. Then the other will come. Okay, this one was deleted. So now there's a gap. So these element will be shifted to left. This will be shifted to left. Okay, for example, it was this way, but now these elements will come here, this element will come here, this element will come here. It will be shifted like that. Then this will be first in first served. It will be served, and it keeps on going like this. This is queue. Okay, but we can, okay, so this is a normal queue, but we can make it circular like this. This is a circular queue. This is a normal queue. It did not make any circular, but these are circular queues. These are all circular queues. So the queue should be managed as a circular queue to avoid moving the position of the items. Avoiding moving the position of the items in the array every time an item is removed. Here what I was doing, it was they were changing the position. This will come there, this will come, they were changing the position. Okay, they were changing the position. But if we try to make a circular queue, it will not remove any, it will not change any position. So this is the circular queue. It's starting from here and then it will come back here. The first come, this is added up, then this one add up, this one add up, this one add up, and this one add up. This is the end. This is the start, this is the end. It's coming back to, it starts, it's circular. circular queue, unlimited it's more like a loop. It forms a loop, start from here, end from here, and then there's a gap to that more, two more can be filled in here. Okay, supposing if we want to delete, we delete this 11, and then the front pointer will come here, it will point to this one, delete, 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 delete. Okay, this is how it is happening. 11 is removed, then 27 is removed, comes in here, the pointer has been changed. But in here it was a different scenario, it was pointing to this one only. Okay, and so this is the queue, and the concept of queue is here. This is a pseudocode. Let's see. Declare queue making an array of 1 to 10. Declare rear pointer, front pointer. Okay, rear and front and end pointer. Queue full, which means is, okay, let's see what is a queue full. Queue full is, okay, this is the length. Queue length is something else, I think. Let's see where it is being used. If queue length is less than queue full, queue length, which means the length, the real, okay, queue full is the limit of the array, and queue full is the actual length of the queue, which is actual present length of queue okay. So if queue length is less than queue full, which means queue is empty, they say the space is available. If queue length is less than queue full, if rear point is less than upper bound, okay, upper bound, I think it's the same thing, queue upper bound or queue length, still of the upper bound or queue full is more like same thing, 10 10, right? If rear pointer is less than upper bound, for example, if we have an array, okay, and this is the front pointer, I have added up, this is a front pointer, this is a rear pointer, and this would be the upper bound, this is the upper bound, and this again would be the queue length, oh sorry, queue full. This would be the front pointer, the end pointer, and the queue length. The queue length is 1. We are keep on adding up. This will be the rear pointer. This is the front pointer. This is the rear pointer, and the queue length will be 2 1 2. Okay. So if the rear pointer is less than upper bound, if the rear pointer hasn't come to here, then rear pointer is equal to rear pointer plus 1. Else, okay. Else, if for example it has been full, then rear pointer is equal to 1. Okay, this is the pseudocode of circular queue. Okay, rear pointer is equal to 1. For example, if rear pointer is here and you're seeing that it has crossed the upper bound, then it will come back to 1, the index 1. So the rear pointer will pointing to rear pointer here, this is the index 1. It's a circular, right? It wasn't here, but then there is no space, then it will come back here, pointing to this index. There's a meaning of this. This is why it said rear point is equal to 1. It will come back here. And if queue length is equal to queue length plus 1, so since we are adding an item, an element, we are included. We are doing include. Okay. Queue length is equal to queue length plus 1. Queue rear pointer. Okay. So pointing to, for example, it was let's say if I want to add an element, so rear pointer will come here, rear pointer will point to this side, queue length will be increment 1 2 3, and queue rear pointer is equal to item, we have put an item here. Okay, else for example, okay, I have made, okay, if queue length is less than queue full, but if queue length is greater than queue full, which means queue is full. Okay, yes, definitely. If for example queue length is less than queue full, then only then this whole code within will run, If it is full, then this will run. Q is full, cannot in queue. Okay, this is the pseudocode of adding an item. Now if you want to delete it, if queue length is equal to 0, then if queue length is all, the queue length is 0, which means there's no elements, which means queue is empty, cannot dequeue, cannot dequeue, cannot inqueue. Okay, but if it is not empty, then item is equal to queue for front pointer. Whenever we try to delete any item, it will start from the front pointer, first come first served. Okay, so front pointer, if front pointer is equal to upper bound, for example, if the front pointer comes here and it crosses the upper bound, then the front pointer will come back here. Keep on, for example, let's say we have these elements and then we get 11, and this is the front pointer. If we want to delete it and it's crossing the upper bound, it will come back here, delete, delete, delete. Okay, circular. So if front pointer is equal to upper bound, then front pointer is equal to 1. Else if it is not, then front pointer is equal to front pointer plus 1, it will come down. Okay, again we have, so if then else, okay, if then else and if, there you go. If then, if it is empty, then queue is empty, else this will run like this. Okay, queue length is equal to queue length minus 1. Obviously, since we are deleting an element inside a queue, the length will also decrease. So there you go, this is queue, this is whole queue, this stack, and this is the linked list that we have discussed. It's part of a data structure, it's part of your this course, E-level Computer Science P2 9618. Okay, so thank you so much, and I'll see you guys in the next video. And in the next video we will cover this, we will cover stepwise refinement, precision function, what the difference, passing parameters, global variables, built-in function, and a lot more in the next video. We have discussed so many things. We have discussed bubble sort, we have discussed all these iterations, and we have discussed a long way from here. Thank you so much for watching. I'll see you guys in the next video. Thank you.